Hello everyone. I hope you guys like exploits, because if not, you might be bored. If you don't want to hang out, that's fine. I won't be offended if you leave. This is the first time I did this specific slide deck. I haven't actually even done a dry run yet, so it might be a bit long. Hopefully we'll get through it in time. But if not, and you gotta go, you gotta go. I won't be mad at you. So let's jump in here. So this talk is lessons learned from researching and exploiting Stagefright. I see there's no water up here. Get some water if we have some. I just want to talk a little bit about some of the things that I learned while writing some exploits for these things. You know, initially when I found these bugs and to even disclose them, I totally didn't even want to write exploits. So my boss encouraged me, and I actually got through it, and wasn't surprised of some of the things I learned. So here's a quick agenda. I will just jump right in here. For those of you who don't know me, I'm Joshua Drake. Go by JDuck on the internet. I've been doing this kind of stuff for quite some time. I'm the guy who found this Stagefright and initially made a big deal about it in the press, and so kind of made it a bigger thing than I don't know, than you might expect. But it's so I'm also the VP of Platform Research at Imperium and lead author for Android Hacker's Handbook, if anybody has read that, and if not, it's getting a little dated now, but it's still quite relevant. And also founder of the DroidSec Research Group, and you can see here some of the places I worked previously. Thank you, HT. You're the man. You are the man. All right, so some of my motivations, and this is a slide that was in kind of my old talk from last year at Black Hat. You know, these are the things I want to do. I want to make mobile devices more secure. I want to make them more safe to carry around. I want to feel safe carrying it around and not feel like somebody's watching me all the time. And I also want to, you know, put the Droid Army to good use. I did a talk 2 years ago about the Droid Army. It's a very, very cool project. And so check that out if you're interested in seeing lots of Android devices all connected up at once. So acknowledgements, I want to take a minute to acknowledge Occupant Labs, where I used to work and originally found some of these bugs, which has now become Optiv, and Zimperium, my current employer, who, like I said, encouraged me to continue working on these bugs and developing them further. And then Amir Etemadi, who I don't know if he's here or not. He was here a little bit ago. But he was instrumental in helping me do some of this bug finding and research. And I also want to thank Colin, Matthew, and Daniel, who were offered their expertise, and especially with Colin and Matthew in the area of cellular network stuff, and with Daniel, some interesting operating system stuff. Also, thank you to the ISSW organizers. This is a great event this year. It's definitely a little bit different than the previous years, and I want to give all these people on the slide a round of applause if you guys are willing. Yeah. Thank you. Okay, so let's jump right into this more stuff. So what is Stagefright? This slide again was one from the old talk, at least the first half. You know, Stagefright is the multimedia framework library, the thing that kind of underpins several or almost all of the multimedia formats that are supported by Android. It's primarily written in C++. It handles all video and audio stuff on the device. It also, you know, of course, provides playback for these the video player or media player. An interesting thing about it on Android is it actually extracts metadata very promiscuously for the gallery and to show kind of what media content is on your device from like a thumbnail point of view. So also Stagefright at this point has its own Wikipedia page where, you know, it's also a big vulnerability that made a big deal, or which was a pretty big deal at the time when we disclosed it. And that was that at the time an attacker could send one or more MMS messages and take control of someone's device without them even knowing potentially. Yeah. So I mentioned here at the bottom to see the talk slides from last year. Those are published, and there's a link at the end that's shortened if you want to take that down. So a brief history, like Stagefright was not always the library that was used. Android originally launched with this thing called OpenCore, but through, within a couple of years, they switched over to the Stagefright library, and it's been the default library for media playback and stuff ever since, and it's still today. So an interesting point about Stagefright and AOSP in general is that it's all open source under a very liberal license. It's very similar to the BSD license in that you can fork it and change the crap out of it, and then you don't even have to release your changed code at all. Because of that, it's found its way into lots of different places. Some of the code was used in Firefox on Windows and OS X and Firefox mobile devices. Also used, in all sort of the forks of Android that come out, like Fire OS or any of the other kind of OEM shipped things. I looked at this initially because of it being in the AOSP base. I knew that it would be in everyone's Android device. I think that's a good area to focus. And then there are some, like CyanogenMod, that don't use Stagefright. They have FFmpeg kind of transplanted to do the media transcoding and stuff. And then Nintendo DS and the Nintendo Wii U were surprisingly using Stagefright code. I had no idea until, at some point somebody's like, hey, we totally hacked the Wii U and we used your bug that you disclosed. I'm like, okay, cool. That's awesome. So a little background information about the system architecture in Android. Android is very modular. Everything, the security model of Android is based on all of these things running under separate users within the Linux kernel. You can see the diagram here where some of the things are shown. The important point here is that Stagefright lives here in the media server component, and specifically from this diagram within the other media services. They didn't quite mention it there, although it's used in the media player as well, as I mentioned. So this service, media server, is a NATM system service that starts at boot up, runs in the background. It's a daemon, if you will, from traditional Unix kind of background point of view. It automatically restarts whenever it crashes because it is spawned from init. It's noted as sort of a core service. If media server disappears or crashes or doesn't come back, then you will no longer have any audio on your device, which is kind of a sad thing if you expect to get a phone ringing or anything like that. And the other big point about media server that I like to make is that the privileges vary a lot, but even on the lowest privilege devices, which is Nexus devices, you all automatically have access to internet, camera, audio, and Bluetooth on all Android devices I tested. Within the Droid Army, 50% of the devices actually gave you the system group, which is a very high privileged group, typically thought to be able to get root very easily from the system group. It's very, very trusted, including tons of places in the AOSP code where there's literally if user ID is system, then don't check anything, just do it. And then on a minority, they have stuff like input where you can synthesize clicks and key presses. The shell group, which is very uncommon to get access to, or the radio group, which would allow you to do stuff like intertwine yourself into phone calls or MMSs and stuff like that. The big point of the slide is that media server is definitely an attractive target. It's kind of in the middle of all the things that are cool going on a phone. So a little bit about what I did last year, kind of a few slides to summarize. I had a limited scope last year when I did the research and when I did the talk. It supports lots and lots of different formats. I only focused on MPEG-4 handling initially, and even then I only focused on the metadata extraction portion, and not even playback of media at all. And then later I looked at ID3 and MP3 handling and tested. In both cases, I tested the stuff all in isolation. So basically removed tons of code and only just tested the crap out of these kind of limited areas. I think this is a better way to find bugs personally, because you're not testing tons of code that doesn't do what you want. So round one of my vulnerability discovery stuff was really kind of using this strategy of fuzz, analyze, audit when you're analyzing the crashes, and then fix the bugs so that you don't find them again and then keep doing that. In round one, we used a totally dumb fuzzer. It was just using like a 60K video file of a cat that's like, "Rah!" or something like that. It's pretty awesome. I have the video, but I don't think it's very easy to play it right now. And so we did the testing through the media scanner component, which is a service that's documented in the Android documentation. It's pretty easy to trigger it. Basically, we're just copying a file onto the device and telling the media scanner to scan it and repeating that over and over again to do the fuzzing. In that round, we found some crashes, but none of them really looked very cool. They all looked really kind of lame crashes. Most of them were crashes where it was doing some checking and then had decided to kind of abort the process because they didn't see what they expected. However, when I looked at the code around there, I discovered 5 vulns in the functions that were where some of these crashes were happening. So I kind of took those, noted down, and then moved on. In round 2, I decided to experiment with American Fuzzy Lop. In that round, I decided to take the Android code, like the AOSP lib Stagefright code, and I removed all of the Android-specific portions of the code just with if-defs. So that it would build on a regular x86 Linux machine. And I ran AFL like using 30, 32 or something full cores. And I think all in all it was something like 6 months of CPU time that I spent on it. Found vulns from round 1, which I was, it's always been a kind of an experiment of mine whenever new things are coming out, new tools to find vulnerabilities. My favorite thing to do is to go and use them to try to find the vulnerabilities that I already know about or that already exist. It's actually kind of interesting. Most of the time, you don't find the vulns even that you know about. But in this case, it did, and it found additional vulnerabilities. And on top of that, it discovered some vulnerabilities that I had seen before that I thought were fixed in Android 5 Lollipop were not actually fixed at all. So that was pretty interesting. So exploit development, after switching jobs and doing some more stuff, my boss encouraged me to write some exploits for these. And so I released one last fall that was just an MPEG-4 generator that generated a file that when you would scan it or play it on a Galaxy Nexus running this really old version of Android would pop you a shell. We're planning to release another one very soon. I'm actually going to hopefully demo that one here live. Let's see if that works. And it's kind of interesting. I'll talk much more about these exploits when we get further down in these slides. I have to go faster. So, impact on the industry. When we first disclosed this, it had a huge positive impact. It totally got the attention of basically everyone whose attention it should have got their attention. Shortly thereafter, I did my talk at Black Hat on, I don't remember which day, but in the morning of that day, the Android security lead guy, Andrew Ludwig, did a talk about all the changes they were announcing for Android, and that included moving to a 30-day patch cycle, which they've been honoring and continuing since then. They also mentioned that other OEMs committed that they were going to do the same thing. They're going to move to a 30-day patch cycle and do disclosures. And so far, I think only Samsung has really been doing anywhere near like the level of effort that Google has been doing. At one point, a representative of HTC on Twitter actually claimed that this 30-day patch cycle, and I used the quotes because that's really what he said. He said, this is unrealistic. I don't see it as unrealistic because you can see already that Google is doing it every month, so I don't see why someone else can't. So some of the devices got updates, but a lot of them didn't. Android is kind of like a complicated ecosystem in that people buy the phones and then the manufacturers don't really support them very well. So you could right now go to like say Walgreens or something and buy like a prepaid phone, and it may or may not have a patch for Stagefright, which is interesting and sad. So the company I work for, what did we do? We created this thing called Zimperian Handset Alliance, which was meant to address the problem where there's all these people who are shipping Android but are not necessarily partners of Google. If you report a bug directly to Google, a vulnerability to them, they'll work with their partners, but they really don't, at the time at least, they really didn't include people like Amazon, for example, or whoever else might have forked Android and just made their own distro of it. And at this point, we've got over 25 carriers and OEMs and vendors that ship various things that depend on Android or just mobile stuff in general. It's pretty cool. We're still continuing with this effort. We also, right before Black Hat, released an app called Stagefright Detector app. It's really just a simple vuln scanner that looks only for the Stagefright bugs that we had disclosed. It tests for 9 CVs, and it does that non-intrusively. We were very careful to work with Google to make sure that we could publish this in the App Store and not get blacklisted or have the app get taken down. The big thing that they cared about was they don't want us crashing media server because obviously you lose audio and all kinds of other stuff. So they didn't want that happening. So we worked around and figured out how to do that without that problem. We collected anonymous data from that, so if you scan your device with it, it just reports back kind of like an anonymized ID and then which CVEs your device is vulnerable to. We did a recent blog post kind of showing some of that data. So also in what I call round 3, we reported in another 10 vulnerabilities, including this one that got dubbed Stagefright 2.0 by all the marketing stuff. After that, I created some CTS tests for the various vulnerabilities and upstream those. Sadly, they got rewritten like 4 times after I sent them in, so I kind of like sad about how it's not actually my code, although my name's still on it. And then we've also added a bunch of detection capabilities to our products to find exploits for this kind of stuff. So Android Security Rewards Program was announced in June. I had reported the original like sort of set of vulnerabilities to them in April, and so I missed it kind of by a couple of months, sadly. But it's still operating today. It's a very good program. The CTS tests I did were stuff that they paid out reward for, and the exploits that we released and we shared with Google, they paid out for that stuff too. So it's a pretty cool program. I really think it's a nice opportunity. You could potentially receive up to $38,000 for a single vulnerability if you do all of the things that they encourage you to do. So the third round work qualified for the bug bounty program, and the original reports did not, unfortunately, although I did get some small bounties from Mozilla and from BlackPhone through BugCrowd. At this point, the total bounty for Stagefright is like over $50,000, and so we'll probably have a nice party at B-Sides Las Vegas. So if you guys are out there, yeah, let's drink some bug bounty money for the win booze. So community efforts, I had expected sort of a response to the talk, and I expected people and even encouraged people in the original talk to go and look more at Stagefright. However, I never expected there to be as many people as have looked, and I certainly didn't expect them to find 110 bugs with 69 CVEs in the last 8 months. If you're interested in more stuff about this other than this talk, there are several good write-ups out there. There's 3 exploits at least published already out there, although I think mine works better, but we'll see. So observations from the Nexus security bulletins. Media server components in particular, there are some that are only elevation of privilege, meaning you're going to have to already be on the device, or the typical attack vector for that is to have a malicious application, which isn't really something I get excited about. I think most savvy people are smart enough not to install some really shady looking application and get owned that way. But there's another thing that I've noticed over the last 8 months is there's been several information disclosures vulnerabilities disclosed through the Nexus security bulletins. However, at this point, it's unclear if any of those could be usable to make a more reliable Stagefright exploit. Really it requires some more research there, I think. So some of the vulnerabilities also live on the libraries that Stagefright depends on. So Stagefright is kind of a middle layer in a way. You have media server, and then you have the media extractor, and then you have the Stagefright that's fulfilling that. But for some of the formats, it actually links into other libraries, like libflac, or there was libsonivox or something. There's been several vulnerabilities published all the way, so it's totally bugs all the way down. So Android N is in preview right now. Android N, they split media server into multiple components, I guess as part of the response to the Stagefright stuff. You can see here we now have an audio server, so hopefully that means if you crash one of these other things, you don't lose your audio anymore. They have a camera server now, and they've kind of split the playback and the extraction into these two components of media codec and media extractor. This media DRM server thing is new. There is also another DRM server that was there before and is still there. So I'm not really sure of all the details of this, but what I did check was that the media codec and media extractor processes you can see at the bottom there, they're only giving you access to a very limited sort of set of groups, unlike before where it was all the stuff, you know. So let's talk about exploitability a little bit. The question, you know, a lot of people have is can you make a really good exploit for Stagefright? Diversity is kind of the first thing that people tout as one of the things that blocks reliable and widespread exploits on Android. I think it's true to some degree. It does complicate things. However, generally all you need to do is find a version of the firmware that you can download. They're all pretty much easy to get. And then it will require some extraction of key details from that firmware. The interesting point here is that for a browser exploit, and I mentioned before the original stuff was MMS, they've mitigated that attack vector, but Android browsers are still totally exposed to this, so just clicking a link anywhere on an Android device could potentially lead you to a Stagefright exploit. So the cool thing is that the browsers are super revealing. You can see here in red, this particular device that I have here, right here, whenever you make a request, will just say, hey, I'm an Nexus 6, and this is my exact firmware revision. And that's the only information you need to go and pull a full sort of full device image down from the internet, and then use that to extract some key details. So crucial components when you're talking about exploitation, you have ASLR, address-based layout randomization. That's a kind of a key mitigation today to make exploits impossible or at least much more difficult. That's usually implemented in the kernel, so that's kind of a key piece. Specifically the entropy and you know, how unpredictable or predictable that is. Then you have the heap implementation. Most of these vulnerabilities were heap-based vulnerabilities, so the heap implementation details within the libc are very crucial to determining if you can exploit it or not. Bam. So mitigation summary. These are kind of like the big mitigations that are always getting in the way of exploits. First of all, you have SC Linux. This really didn't apply in the first exploit I wrote because SC Linux didn't even exist at that time for that device. But the second exploit I wrote, SC Linux was there, but it didn't really get in the way until after I already had arbitrary code execution. So that means it was limiting my payload, but it didn't in any way block exploitation. So stack cookies don't come into play. These are heap vulnerabilities. Fortify source doesn't really work when you're dealing with dynamically sized variables. There's no way for it to encode that checking into the program at compile time, so that doesn't really come into play. ASLR was really only something that was even the smallest concern on devices with Android 4.1 or newer. So that didn't apply to the first round, although it definitely did to the first exploit, but definitely did to the second one. NX, you know, it's a great tool. However, like we've been able to bypass NX ever since really it came out. Like it just requires a different way of thinking about it. So NX and ASLR go hand in hand. It's like if you don't have ASLR but you have NX, then you really might as well not even bother having NX. It really doesn't help you much. But if you have them together, it makes things quite a bit more complicated. The last line here is a GCC new mitigation. At some point, I think in GCC 4.9, they added a checking for whenever you use the new with the brackets, so to allocate an array. And they used to have an integer overflow whenever you would allocate too many of whatever size object. But they've actually instrumented the code at compile time like as a mitigation, and it blocked some of the vulnerabilities that I had discovered and reported. So I mentioned ASLR before a couple times. This is really the only challenge when it comes to writing an exploit for a Stagefright bug. The rest of it is just kind of tedium that we'll get into. I managed to really fully bypass ASLR and ICS both on the, fully bypass ASLR on the old device, which had a key like kind of weakness. And then even on Lollipop, I was able to bypass the ASLR pretty easily. So let's just get through, let's see, newer Heap is weaker. So that the new version of Android switched their Heap implementation from DL malloc to JE malloc. And in doing that, they've weakened their operating system significantly, I think, especially for heap vulnerabilities. First of all, there's less entropy in the addresses whenever they're allocated and handed out to the call sites for allocation. So that means it's easier to guess wherever your stuff that you're getting into memory is. Also, JE malloc has no inline metadata between chunks. So if you have like 10, 20 byte chunks, then they're all going to be packed right next to each other. That means if there's an overflow in one of those, then it's only going to hit application data. It's not going to hit any data that's used by the heap implementation. And that's important. Like they do have inline metadata in DL malloc, and they have several kind of validations whenever they're walking through the chunks in the heap. And if any of those validations fail, then it will crash the process intentionally to try to save you from getting owned. So as a result, it's totally easier. And if I had known that it was easier, I totally would have wrote the exploit for Lollipop before I wrote this IceCreamSandwich exploit, but that's lessons learned, right? All right, so let's walk through the first exploit that I released for IceCreamSandwich. This vulnerability, the root cause of it is an integer overflow, as I mentioned, with the new bracket operator. So this vulnerability, even if it were present on Lollipop, would not be exploitable due to the change in the GCC mitigation. However, like you can see here, like they're allocating an array of sample to chunk entry objects using this mnum sample to chunk offsets, which is just read straight out of the file. If there was a large enough one, then the allocation, the mathematics before the allocation of the size wraps becomes too small. However, like this in itself is not necessarily enough to be a vulnerability. I've seen a lot of times where they do this, and then they use that resulting size for the multiplication to also as for copying. And so they end up allocating too small, but then they also end up copying too small. So there's no vulnerability there. But in this case, the loop bounds was that huge number, and so they're basically looping forever-ish, reading individual entries and storing them into the fields within each entry. So what does this leave us with? So the primitives of this vulnerability and the things that kind of get in the way, we already know we can allocate a buffer that's too small. We know we can copy more than we allocated space for. And we know from this, when it's reading the stuff from the file, that if the read fails, then we'll exit this function before the loop goes to a really huge number and reads out of bounds memory and crashes or something like that. That's a less than ideal situation for a successful exploit. So the terminating is both good and bad. It means we won't crash whenever it's looping on this giant array bounds. However, and so that means we can stop whenever we want just by truncating the file. However, that means we lose control of the parser at that moment. So whatever's going to happen, hopefully it happens when it's wrapping up its processing. Otherwise, you've got some corruption, and you no longer are really talking to the service anymore. And I mentioned it's not a local exploit, but I mentioned the service because that's still what's happening internal to Android whenever things are going. So the first, also we noticed that the first 32-bit value there can't be, it can't be 0. So if it's 0, this check macro is one of those things where it will crash the process intentionally when it fails this validation. That's actually one of the exact lines where it was crashing in our first round of fuzzing. So that's the kind of bugs we found initially. Because of that math, it means we can write 0, but we can't write -1. I don't see that as a big setback at all. It really never came into play. You just can't put 0 in there; it'll crash. So the next question, when you're writing an exploit and you can overflow it, you can sort of stop overflowing whenever you want. The next question is, what do you want to overwrite? And so the methodology I typically use for that is to hook up a debugger, kind of experiment with allocation size. Depending on what size you allocate, you're going to end up kind of in a different area of the heap. You might be close to one object or another type of object, depending on sizes. Experimenting with the overflow amount, because you might end up right next to something you want to hit, or you might end up kind of a little bit further away, and so you want to write more just to get there. And then just see how the process crashes, kind of walk through after the corruption happens, walk through and see what's going on. It's a C++ program, so the important thing to look for is kind of like objects that have already been allocated that might be able to be corrupted if you get the right layout of the heap. And I usually take a sort of a most frequent to least frequent type of approach to that. So I'll run a whole bunch of tests to see how it's crashing, and then kind of bin those crashes and see which ones are happening most often to kind of prioritize how I look at the code. And then ultimately I ended up with a technique for this one that was first published in Jan Horn's CVE 2014 7911 exploit. That was a local vulnerability where there was a deserialization of a Java object that trusted a value from the object, and then it would end up calling this decstrong function, which in turn will call a function pointer within this ref base object. So the next thing is, you want to make a reliable exploit. You don't want to make your exploit just work like 1 out of 1,000,000 times or 1 out of 200 times or something like that. You want it to work hopefully every time. And so you really have to get into heap feng shui. You have to really learn how can the heap be laid out, how can you influence the way it's laid out, how can you control allocations and freeze within the thing you're targeting. And one of the things that I ran into on this device in writing this exploit was that the heap use in media server was very noisy. And what I mean there is I mentioned a media server is doing so many things for the device. One of those things is just sitting there waiting for kind of broadcast events. And those happen all the time in the background. There's components, broadcasting stuff, and that all plays with the heap. So that can make things really crashy whenever you're trying to get your exploit going. All right, so one of the things also about the MPEG-4 code was that there were very limited opportunities for freeing data. You could totally allocate lots of different ways, as much stuff as you wanted, filled with stuff that you controlled, but getting stuff freed, it was much harder to do. As you can imagine, it's loading a file, so there's not really a lot of freeing going on when you're loading a file, usually. However, there's these metadata items, and this is an excerpt from that exploit with some comments that I don't think were in the released one. But the metadata items are freed and reallocated if they need to grow. So there's a check in this function call that they use called set data or set metadata or something like that, where it says if this is bigger than what space I have for, then free that one and make a new one. Otherwise, it'll just copy the data into the existing buffer and replace it. So we can use this to do some heap feng shui. And what I ended up figuring out by doing a lot of testing was that the best thing to try to overwrite was a track object. In MPEG-4, that track is just another sort of another atom within the file. So you just put track in there and you can set it up good. So the reliability in one attempt was not super great. It was about 20% due to the noise. This is, again, with IceCreamSandwich and the DL-malloc allocator. So with that, things that were happening usually were some broadcast event happened, which then triggered using the heap, which then triggered the metadata validation and crashed the process. There were a lot of those crashes. They were really annoying. However, if we succeed, and that's kind of the idea with an unreliable exploit to move forward, you kind of have to assume you're going to succeed. And if we assume that we succeed, then we know we're going to get control of one of these ref base objects, which is within the track. And you can see the assembly code here where it's loading at the beginning this mrefs object, which is part of the ref base object member. It's a member variable of it. Then it calls this atomic decrement here, And that function basically, subtracts 1 from the number and then returns the original number. So then it checks to see if it's 0, meaning we just decremented it to 0 now. And so then if it is 0, then it'll come down here and load this function pointer through this kind of series of dereferences, and then go ahead and call it. So that's kind of like the gist of how it gets from the overflow buffer to code execution. But the problem is we have to control this value, and we have to make sure it's 1 whenever it's going to get decremented. And we have to control all these dereferences, or otherwise we're going to crash. So how do we do that? We start, and if we go back just briefly, like this thing right here is the first thing where it would crash if you just wrote it over with crap, like 41s or FFs or whatever. And so we need something so that this won't crash first of all, and then we can worry about all these other things later. So the answer to that is to use a heap spray. A heap spraying is a very kind of brute technique, if you will. It's very noisy and very resource intensive, but it's very effective, especially with 32-bit processes. You can totally spray tons and tons of memory. And in this case, I think in this case I was doing stuff like 4 megabytes, or in the event of sending it over MMS, it was kind of limited by the network, so I think it was 2 megabytes there, or other attack vectors are like USB, where you can use a much larger file, or SD card or whatever. So the cool thing here is that we can make huge contiguous blocks of memory very easily through lots of different MPEG-4 chunks. And with the heap implementation details, if we make large allocations like that, we know that it's going to get serviced with mmap directly. So we're not going to try to create some kind of regular heap chunk that has inline metadata and is kind of scattered among the other ones. Instead, we're just going to get a huge chunk where there's nothing on either side of it, and it's just meant to contain only our stuff. And when you use that, what you end up with an mmap allocation is you know that it's going to return a pointer that's aligned on a page boundary. So that means 4,096 bytes is a page size. So we know that every 4,096 bytes is going to be predictable, and it's going to be aligned. So that already removes something like 3 to 5 bits. I don't know the exact number right off the top of my head, but it already removes a bunch of the ASLR for us. And then through creating a whole bunch of stuff, a whole bunch of page. So the heap spray is basically a single page, and we're like, well, we know we're going to control all of the contents of this single page, and then we know we can repeat it over and over and over and over and over again for as big as we make this chunk that we put it into. From there, we can just try to guess an address that falls anywhere within that, and then if it's anywhere within that, then we've won. We can pass all the checks that we need to. So in doing this, one of the things that I did to make it more reliable was just a simple statistical analysis. I put sort of a breakpoint that would print where the buffer, the address that it was allocated at, just ran it for like thousands of times, and again binned the results and came up with sort of a sliding window where I picked a number that would more than likely be always in that sliding window, and that worked out pretty well. So from there, now we have control of the program counter, and so from here it's doing ROP, return-oriented programming, and in the case of this device, the ROP chain was super duper simple. This is literally the entire ROP chain, kind of spelled out, and it was super simple. Like this pivot gadget was already documented in our book, which was cool. That was cool to be writing an exploit and pick up my own book that we worked on and flip through it and be like, hey, that will work for this exploit, and then put it in an exploit. So that was cool. Shout outs to Georg Wachurski for putting that in the book and for finding that. And then just a pop PC gadget just to continue things and align the stack a little better. And then this mprotect gadget is actually like one of the functions within this linker that's not randomized, meaning it's completely predictable where that sits. And actually all of these gadgets are from the linker. So it's very simple. We know exactly where it is. We know all the code, and it has mprotect already in it, which is great. So these gadgets, at the end of this, like we now have an RWX memory segment. Like we basically just use the same address we guessed for the spray, and we say, let's make that RWX now. And so now we can execute whatever payload we put in there, any shellcode. So in this case, I used a very simple Metasploit payload that was slightly modified. The things I modified, are you kidding me? Is it one of you guys? No, I can't talk to him right now. What a ball. I would have put my phone on airplane mode, but I need it for the demo. Are you kidding me? Jesus Christ. Okay, sorry guys. Always put your phone in airplane mode when you speak. So the modifications were a call to fork to escape from the original media server process that we just totally blew our overflow all over its memories. And then we want to exit that process so that it can respawn. And you can, all right, I'm going to answer this. Watch this stupid shit. Oh, now Amir's calling me. You punk. I hate you with the most love I can. So, we want to exit that process so we don't lose our audio and everything continues on as we hope. And then we do a set SID to create a new sort of process session, and that's so that we can send signals and stuff without interrupting the original media server once it respawns. So then we pass a sane environment when we execute the shell, and this is kind of like an unnecessary thing. However, if anybody's ever popped a shell on an Android device and you're like, ID, it doesn't do anything. It's like unknown, it doesn't exist because the path is totally like crappy by default. So I basically just do this to send a path where I can actually reach some of the programs that are useful. Totally a convenience thing. So let's talk about the other exploit. That's a more fun one. So this one was done on Lollipop. Actually, this phone here is the exact phone I used to do this development. This vulnerability is also an integer overflow, but this time in the TX3G handling. You can see the code here where it's using this meta object within the last track that it encountered to find a text format data, and these are reference parameters where these are filled in by this call. So then you can see another thing here, although this one is different. We have just a character buffer, and it uses these two values, which one of them it read from here, to figure out how much to allocate. Interesting thing about this is it's not affected by the GCC mitigation because the object size is 1, and the overflow actually happens before it even calls any of that code. So chunk size is fully controlled by you when you put atoms into an MPEG-4 file. It's basically like a length and then a tag and then the data. So you control that length and you can set it to whatever you want, and it ends up in this variable. At the end of it once it's done its work, it does some copying in between here, which we'll look at in a minute. Then it puts the resulting buffer back in there. So what we have here is an accumulator. Every time a TX3G chunk is encountered, it'll take any TX3G data it already has and add this onto the end of it. So with a second chunk, if we have the first one, we put something in there, and then a second one, we can actually make this number non-zero, and then this number some giant number. When you add them together, you get a number that's smaller than you expect. So, but the important thing is here is how is this buffer used? As we saw before, this isn't enough. If they are allocating this and then they don't even use it, or if they decide to again add size and chunk together and do a memcopy or something, then we're not going to have a vulnerability. So let's look at that. Okay, so I mentioned that part, and here's the code that was kind of cut out. So we have this memcopy, so that's what they're doing, and you can see here they used the size that was already there. So when they first allocate the buffer, they'll copy into the temporary buffer the stuff that it already had, and then it will use this readout function to read the rest of the stuff. So the cool thing about this vulnerability is we basically control everything. We control this size, we control that size, we control the stuff that's in here, we control the stuff that's in there. We control basically everything. And the cool thing, and this is from the exploit, is we can control the allocation size and the overflow length totally independently using just some simple math. So the question again, what to smash? Just playing around with it yielded a bunch of different stuff. The first exploit I wrote for this vulnerability actually was using the media scanner. And in that case, I used the same technique as the old exploit to overwrite a ref base in a track, and that worked okay. Keep in mind that this is a JE malloc now, so with JE malloc, there's, again, nothing in between the chunks. So that means, once you smash a chunk, you're smashing over all kinds of stuff that's in the same size class. There is there's a great paper that's referenced here in the slides, one of these slides, that talks about JE malloc. I read it like twice while writing the exploit, and at one point when I read it, I just totally had an awesome epiphany and did something. I wrote a few lines of code after having this epiphany, and then tested the exploit, and the thing did exactly what I thought it would do, and it was one of those cool moments when you're writing an exploit where, hey, will this work? Oh wow, it did work. I thought it was going to crash again or something. So we control all the stuff, and then we also no longer have to deal with these crashes from the heap corruption detection. So that makes for a much more reliable exploit. So for the feng shui in this case, we needed to get the buffer before this M data source, and if we can go up here, the idea is this will cause the overflow, because this is too small. This is the stuff that we had before, and this is the size of it. This is smaller than that, then it's going to be a problem, right? So the ultimate goal, the best case scenario, is when this happens, it overwrites the contents of this, which then will dereference and use the readat method from a vtable that we totally control. So in order to do that, this is kind of what I came up with when I had that epiphany from reading this paper. I was like, hey, I can make this cover chunk around the same size as this data source, and then I can allocate a data source. What? I know this is right, but it seems weird to me right now. So so the idea is we allocate some chunks that are around the same size as the data source. Then we allocate the data source. It gets set to M data source in the code. I don't have a slide with that code, I don't think, but you can totally check it out in AOSP. And then you free the first one, which basically will make a hole right before this. And then we allocate a chunk that we can overflow with the vulnerability of using the same size, which then will get put in this hole. And when we overflow it, it'll be boom, MPEG data source is ours. So that works out really well. This was the moment where I was like, hey, if I do the cover, and then I wrote the code, and hey, wow, it works every freaking time. So if all goes well, we control this data source, we control the vtable, all the member function, or all the member variables. And again, like last time, we use a heap spray to gain control reliably and to get past ASLR in the initial stage. So it's the same strategy there. We have a single large chunk that we spray that's, again, pages one after another. JE malloc, although it's much different, it still falls back to mmap for huge chunks like that. And in this case, in this exploit, a browser-based exploit, I used a 16 megabyte AVCC chunk to do that. And in my testing, it was 99% reliable. So whenever I was testing this thing, like every time I sent it at the phone, I had control of, it always landed in the stuff I controlled. And in fact, always had the PC value that was exactly what I expected it to be. But as we all know, like sending PC is not quite enough to have a working exploit. So what do we have to do next? Because of NX and ASLR and everything, we have to do some stack pivoting. To do ROP, you need to have control of what the stack pointer points at. So we need to get that to happen to move on. So in Android 5.1, which I was using, it no longer had a predictable linker. Everything was really randomized. All the code was not in a predictable location. This Google wrote a nice blog about this vulnerability, or a variant of this vulnerability, and they said that in their testing they got 1 in 256 chance of guessing one of these code locations. Now that's less than 1%. I think it actually comes out even less than 0.5%. It's something like 0.39% or something. So that's awful. I did not know this is the case when I wrote my exploit. Actually, they published that blog like 5 days after I finished this exploit. So that was kind of disheartening, but whatever. And so, this is terrible. Like 1 in 256, you can't base anything on that. And not a reliable exploit. So Daniel McKay, who does Copperhead OS, Copperhead Security, he was like, hey, why don't you use a DL Open library? I was like, that makes sense. There are a lot of libraries in Media Server that are DL Open, so I'll just look for a huge one. What I came up with was this Widevine streaming library. It's the biggest one that you can find, sort of getting loaded by Media Server. And the cool thing is because this is a proprietary component, it basically never changes. So I ported this exploit, I wrote it on this phone, ported it to a Nexus 5, and I had to know it changed nothing in the ROP chain at all. It was exactly the same. And the other things because it's so big, it means that it has limited places in the address space where it can be loaded. It can't just be stuck in between, 2 places where it's only got like 8K or something. It needs to have 2.4 megabytes in a row in order to load it somewhere. Something I haven't tested is whether or not I can use some more spraying or something to constrain the options for where it might get loaded better to improve reliability. But I'm pretty happy with this 38% for a single attempt reliability. It's pretty nice, but through the browser or previously through MMS before they fixed that attack vector, you could still just try over and over again. So even if this was like the 1%, which Google had, you can just keep trying and trying until it works. It's just a matter of time. Yeah. So the stack pivot in this case is a lot more complicated because of the way that we're dropped because of the context when we gain control of PC. So I had to do like this 3-stage ROP chain, which is kind of crazy. I don't think anyone's ever talked about a 3-stage stack pivot. But that's what I ended up having to do, and it works really well, so that's great. Everything is very indirect, so ASLR is not involved, and it's really nice. So after that, we launched a ROP chain. Again, we have a ROP stager that makes our page that we guessed RWX, and then runs the shell code. Now the difference here is because I based it on the Widevine library, not the linker, and it also does this awesome stuff where it's looking up the base of libc based on an import, a function, the socket function, which is used by the Widevine library. It's a streaming library after all. And so, we will read that using ROP gadgets and then subtract something. It's all happening down here where it subtracts the values, and then this gives you libc's base. And then you add some stuff together to get the mprotect function. So doing this little dance, you definitely have a very highly reliable sort of ROP chain. And the only variables here really are these 2 offsets within libc. You have to know how far in is socket and how far in is mprotect to do the arithmetic. But as I said before, the streaming library doesn't really change. So all these other gadgets that are here are all the same every time. I have not seen a device yet where those are not available or in a different place. So the payload, at this point when I was developing the exploit, I got to the point where I was like, okay, sweet, all right, ROP's working, I got RWX, I'm totally going to jump to some shell code. Like, what should I do? I was like, I'll just run a shell just like last time. I tried the same payload. What? Doesn't work. Well, it turns out Media Server on Nexus devices, starting with Android 5, the SC Linux policy does not allow you to execute anything. Okay, that's probably good. The thing that does audio and extracts media probably doesn't need to run any external programs, so it should not be allowed to do that. It turns out that on some devices they've relaxed this policy. Samsung, come on. So, but for this device that I was working on, I had to work around this. And so what I did was took this kernel exploit, the ping pong root exploit, read all the documentation about it, developed my own implementation of it, and then translated that into assembly and shellcode using object dump. Now, I don't recommend doing object dump. I had to do a lot of manual fix-ups to labels and offsets in the code, and that took a lot. I think it took like 2 or 3 days for me to like actually get this translated into assembly without error. If I were going to do it again, I totally would do GCC-S because that actually includes all the labels and like is very like nice. But I didn't have this idea until after 3 days or so went by, and I'm like, damn it, did it the hard way. All right, but so the payload of the once we get kernel code execution is simply just to take SE Linux and put it into permissive mode. So we do that and then we spawn a shell. So what does that mean? It means our browser gives us remote kernel. That's awesome. Let's try to do the demo. Let me see. I think I have like a few more slides. Again, you guys are welcome to peace out if you don't want to watch or want to get out, want to go drink beer or whatever. I have no idea if this is going to work, but earlier it worked twice. So I'm just opening the browser, and the browser had the link already saved in there, so it just opens like, kind of like the home page. And you can see already the awesome information it's giving to, oh, look at that. So you can see all the awesome information it's giving in the user agent. You can see requests first from the browser and then from the Stagefright library. They both are asking for the file. And then you can see here that we totally have root. So, I would have been happy without root, but since you made me get root, then cool, got root. So let's go back to the slides. There we go. Now I can put in airplane mode and people can stop freaking calling me. What is it? Oh yeah. Okay. So a note on this CV. So this CV, you know, I'm a little ashamed of this, but it's just the way things went down. In this, I was mentioning before, this CV, 3824. So 3864 is basically the same vulnerability-ish, but there's something I missed. So this code here in this block is the exact patch that I submitted to AOSP. And it looked pretty good to me at the time. It made my fuzzer stop finding the bugs. And that was kind of my process, and so you know, I didn't really analyze it super deeply. I just wanted to get the crashes to go away so I could start my fuzzer again. And so a guy that worked at Exodus, Jordan, does anybody know how to say his name? Starts with G. Grusk, I don't know. Grusk, it's like a long, complicated French name. What? Grushko? All right, there we go. So he actually wrote this nice blog post saying, oh, hey, JDuck, you totally screwed up and missed this. And they dropped this totally 0-day on the Android security team, which was kind of cool and kind of not cool, but, you know, I don't work there, so I don't care. I like full disclosure sometimes. I think they did it full disclosure because they reported it to the Android security program, the reward program, and they were like, oh, yeah, we already know about this vulnerability. And they're like, oh, cool, now everyone's going to know about it. It's one way to handle that situation. So the interesting thing here is can you guys see this in red or not? That's third row saying, barely. Is it better in the back? Here, okay, let's do this. So somewhere I have this window, and I have no idea. Oh, there we go. That's good. Can you guys see all my cool stuff now? So we'll go over here. Is this the right one? Yeah, that's the right one. So these slides are all written in Markdown, so that's awesome. So that's not the red we want. We want this red. So let's make it orange. Let's see if that works. Oh, my presentation timer totally just started over, but I know I'm over time already. So one of these buttons goes back to the slides. Oh, that's not the slides. Where the fuck are they? Oh, they're back here. Okay, that's weird. All right, now you guys can read that, right? All right. So, on the fly, presentation fixing. Markdown is nice. So you can see here, these are the only changes necessary really to change from the exploit for this 3824 into 3864. All you have to do is instead of doing a long with TX3G and the data, you do a long with one TX3G and then a huge 64-bit number and then this data. And so you just put a 1 here and make it 64-bit instead of this, and it works great. So the Metasploit module that we're working on, as you can see, this exploit is rather complicated and unfortunately does not fit well into the Metasploit paradigm at this point. I don't know how many people have written exploit modules for Metasploit in here. I see 2. Okay. Well, having a framework is great until your scenario, that's 3, right? So until your scenario no longer fits the framework, and then you have to do a lot of heavy lifting. So thankfully, Brent Cook and some other guys at Rapid7 are working with me to try to get some of that heavy lifting done and make this work a little better for Android. And the plan there is to use 3864 as the exploit. Once we get a base, once we get the exploit in Metasploit working on this device, the plan then is just to go into scale mode. And so we're going to look for as many devices as we can find, as many firmwares as we can get, and make the exploit work basically as ubiquitously as we can. So that will be cool. If you want to help with that, reach out to me on the IRC, or the Twitters, and I can help you figure out what to do. So the other thing, so there's this Stagefright 2.0, and when we initially went public with that, some of the people looked at the details and they were totally like, is that even exploitable? And that's a good question. And so I had to investigate it, of course. So this one is a very weird situation where they assigned 2 CVEs because there were 2 kind of bad things that happened. Like, first of all, this CV3867 happened during ID3 parsing, which you can reach through an MP3 or an MP4 file. Ended up passing a -1 length to a constructor for a string. I don't know if you can really consider that a vulnerability by itself, but they certainly determined that that is not something that should happen. Like, this length value calculation was an integer underflow that led to this -1, and so they were like, let's now check and not have that root cause of ending up with -1. So that by itself really kind of eliminated the vulnerability, but that doesn't matter that much because the second one is in libutils in the string 8 class, which is a very core sort of native code class for all of Android. And it's open source again, and it's a library of its own, so God knows maybe somebody used libutils to create their own whatever. So they have to kind of create a CVE for this one, especially for itself, by itself, to track it properly. So in that case, and I don't have the code here, but it basically just took the length value that this was passing to that function and added 1 to it, which you can see -1 plus 1 is 0. So then it would allocate a 0-byte buffer, and then it would copy the string data into it. It's a constructor after all. It's making an object from a flat string. And then it would, if it survived this, which you'd think that it wouldn't survive this ever, then it would do this. It would set a 0 at the end. It's a string. It has to have a 0 at the end, right? So what is the feasibility? Android devices are totally weird, and we mentioned the diversity before, so that it goes both ways. The diversity is somewhat of a defense, it's somewhat of a helpful quality, but it also sometimes will bite you in the ass. So when I tested this, just a simple kind of memcopy program on all the Droid Army, what I found was basically 2 groups of things. Like, many of them would totally crash trying to copy off the end of memory. That's expected. That's what you would think when you see memcopy with a -1 length. However, some of the devices use this super cool optimized memcopy implementation that's written in assembly, and in that case, they only wrote 3 bytes and then returned. Oh, okay, yeah, memcopy -1, totally expect 3 bytes to be written. And then it would write this -1 on return, the null to the -1 array index on return. So you basically end up with a situation where you have a 0-byte allocation getting 4 bytes written kind of misaligned to the beginning of it. I was pretty surprised by that, and it's kind of neat. So the other thing about this, memcopy -1 is, that's copying a lot of memory. It turns out, because the media server is multi-threaded and a lot of stuff is going on, we mentioned before the noise. That noise is still happening. However, it's easier to avoid it getting in your way with JE malloc. but it's still happening, and so that means there are threads firing and doing all kinds of cool stuff on broadcast. And if this wild copy is going on and one of those things happens, there's a chance, a decent chance, since you're copying over everything, that it might use that corrupt data to do something. And when I experimented with it, with this vulnerability, I actually witnessed exactly that. So I didn't even try hard, like I just had a simple trigger file that just copied tons of data. And I tried it on the device, and it crashed with PC control, like immediately. I was like, oh, okay. So yes, this one's exploitable, guys. Yeah, I think so. However, I haven't gone any further than that with this vulnerability. The reliability kind of seems like kind of low on this, and you know, maybe I'll get around to writing an exploit for this at some point, but I'd really rather focus on proving out the possibility of an Android exploit that works on tons and tons of devices instead at this point. So conclusions, this is totally the next to last slide. So key takeaways, and it's probably, no, if it's on the screen, cool. So, you know, if you're going to change your heap implementation in your OS, you may want to have the security guys take a look at that and make a recommendation whether you should do that or not. Performance is not everything, especially if it's kind of on a thing where you have all of your important information on it. Other takeaways here is, you know, if you're writing an exploit, sometimes it pays to just sit back and think, hey, wait a minute. I can control this and that and this, but I'm hitting against this wall. Is there a different way I can go? Can I maybe control something in the environment? Can I do something a little bit differently? You know, can I allocate some extra stuff, or like open some sockets, or God knows, you know, whatever it is you can do. Can I do something that's normal functionality that will in some way help me make the exploit either more reliable or more successful in general? Diversity is a thorn, but you know, it can be dealt with. It's a scale issue. It's not really a mitigation. It's a scale issue. I mean, at this point, I have every Nexus firmware on my machine, and I think that directory is 260 gigabytes or something like that. And so I think I can compress that down smaller, but it doesn't matter. It doesn't need to be. Write a script one time that extracts the key details from 260 gigs worth of firmwares and run it once. Then you have all the data, you put it all in the module, it's all done, right? So maybe it's a thorn, but it's definitely not something that's not something you can't overcome. And again here, the Android browsers, they're so helpful with this, right? So you can totally have a good time. I believe you can change your user agent in the settings. I recommend doing that. At least then they have a harder chance of figuring out how to deliver, which version of their exploit to deliver. So mitigations are totally not a silver bullet, as we see here, ASLR, SE Linux, all the things that were potentially in the way. There's always ways around mitigations. While some mitigations can stop, without a doubt, some classes of vulnerabilities, particularly on Android, like stack buffer overflows are pretty like boring most of the time. You know, they're not a silver bullet. In this case, you have multiple attempts, so like they're really not helping you. It's a statistical game at that point. So finally, vendors in using Android or shipping Android, they totally need to be more proactive. I think, you know, I've seen some press articles where some OEMs have totally been like, Stagefright, oh, whatever, yeah, that's totally not going to get exploited. Okay, guys, yeah, maybe it will. So, you know, also they need to be more aggressive at getting the fixes out there. I mean, if the fix is available, why the hell isn't it out there? You know, like, get it out there. Come on. And then the Android codebase totally needs some more attention. This is one library. I think the directory for this library is like, I don't know, 5 megs or something. Well, AOSP is like 20 gigs, so you might want to look around in there, especially in sort of the native code areas. And finally, bug bounty money for the win. So with that, thank you guys for enduring my 62.5 minutes of BS. If you have any questions, we have some microphones. or we can ask me whenever. Totally. Okay, so I either did really bad or really well. So thank you, guys. Those of you who called me during the talk are totally getting reprimanded later.